Ooh, hey, this guy Riemann Sum, or this guy Riemann, his name isn't Riemann Sum, that would have been weird. This guy Riemann pops up. Didn't I mention him yesterday?
No.
Okay, so this guy's a mathematician. He looks at the stuff that Euclid, not Euclid, what's the other guy's name?
Pythagoras?
No. The guy did Newton. Thank you, Newton and Leibniz. And he looks at the integral stuff that they did with the delta x's, the stuff we've already done with the rectangles, and he proposes a simple idea. Why do the rectangles all have to be the same width? Because you saw in some of the pictures that you drew yesterday and some of the pictures I drew already, if the rectangles weren't the same width, we could adjust it to fit the graph and get a more accurate answer. Okay, so that's what Riemann did. It's about the only thing he did. And because of that, he got really popular. We'll skip all this stuff. Yeah, so we're going to do some mad geometry skill work today. All right, so this is all notation. You're going to love this one. What's that big bold thing called?
Sigma?
It is a sigma.
Oh,
Yeah.
I was gonna say alpha.
No, alpha's capital A. And lowercase alpha is a fishy.
Oh,
Then you got the fishy and then the fishy on its head, the gamma is lowercase gamma. Uppercase gamma is, looks like a T that somebody lopped off the left-hand side of the top. We'll get there. You'll learn them all. By the end of this class, you'll have it all under control. You're gonna love it. Anybody remember what the sigma does in math?
Limit?
What's that, John?
It's a repeated, like, function.
Close.
Is it a sum?
It is a sum, correct. It adds up a bunch of things. All that notation is saying is something really simple. Take delta x, which we know represents what? Width of the rectangle. You're right, change in x, which is the width of our rectangle, and multiply it by f of c. Well, what's c? We've learned already that c is just some random number that we throw in the graph. What's f of c? F of c becomes the height of the rectangle. So that's a fancy way of saying what we've already done. Find the area of one rectangle, this initial rectangle, and then add up all those areas. And when you're done, you got the area under the curve. Okay, so the fancy sigma just says add them up. From the initial rectangle all the way up to the nth rectangle, depending on how many rectangles you want to do. Okay, not too intimidating, right?
No.
Okay. And we don't do too much with that. There is a whole slice of calculus that we don't do in AB, but they do in BC that involves working with summations and notation, and it's enough to make you cry. So we're just going to skip it. You can do it on your own time if you like. Okay, so that's what Riemann said. What if they're not all the same width? Something like that. And you can color them if you like. Skinny one over here in yellow on the left, and then big fat green one, and a blue and a red one. I'll give you that area. Still a lousy estimate because we got a big wasted space above. Yo.
So like I understand this, but like you can still keep them all the same width.
Sure.
Regardless.
Sure.
Like you could, if that's like point, like you can make that half somehow and then have less rectangles. So what's the point of this? Is this just like proving the idea that they can be different?
Our ultimate goal is to get as close to the actual answer as possible, right?
Yeah, but you can do that
And-
using the same, right?
Sure.
So is this just basically saying like the same idea applies, but
Right.
if they're
He just wanted to be a pita and change the width of the rect. You know what pita stands for, right?
No.
Yeah.
Pain in the butt.
That'd be painful.
That's really funny.
You'll get it later.
Yeah, it'd be
Okay.
pain in the
So he just wanted to be difficult and change the width of the rectangles.
just to be different.
Well, he got a theorem named after himself.
Like this is so, okay.
I mean, he's kind of like the guy that just stands next to you and does this forever. Eventually, you're gonna listen to what he has to say because he's driving you crazy. He kind of did the same. Hey, what if we make the rectangles different widths? Can we make the rectangles go away? Can we make the rectangles different widths? What do you think if we make the right? It's irritating as hell, right? So they go, okay, fine. We'll name it after you. We'll try it.
What if we use hexagons?
Don't start with me, mister. Let's use circles. Okay, now things get weird. So Riemann needed some notation to represent what he was doing. So he has delta x, sorry, but he changes delta x. Well, first of all, he calls delta x a partition, which we would know just as rectangles. And then he gets this notation over here, which looks like a double absolute value bar with a delta, and says, okay, I've got all these different rectangles. I'm going to find the biggest, widest, fattest rectangle. You with me? That's called the norm of the partition. Find the biggest one. We don't care about the small ones, just the big ones. And then that stuff at the bottom is what we talked about yesterday. I think it was you, Brennan, that said increase the number of rectangles.
Oh,
Right?
yeah.
Yeah. So if we want to get as accurate an answer as possible, we have two options. Increase the number of rectangles or shrink the width of the rectangles. They both achieve the same results. So we had n going to infinity, or in this case, delta x going to 0. But instead of delta x, we're going to use this norm of the partition. Okay, I kind of like the fact that the word limit is there. Beautiful.
And the arrow.
All right, does that make sense? If I got a bunch of rectangles, some skinny ones, some fat ones, and I shrink them all at the same rate, if I just shrink the biggest one to 0, by the time the biggest one's gotten to 0, all the others are to 0. We're good on that idea? Okay. And, yeah,
So is the norm of the partition so it's the largest width?
yeah. So for instance, what color is the norm of the partitions?
Green.
Green. And if I shrink the width of green, well, if I shrink all the rectangles at the same speed, and green is the widest, by the time green gets to 0, everything else is going to have gone to 0. And that will give us as accurate an answer as possible. So that other bunch of calculus that I was talking about then starts looking at this crazy thing and actually puts functions in there. So put in an x cubed plus 2x minus 3, and then you have to start doing some notation to find out what those are, and it gets really ugly, and we don't want to do that. So we're going to change the rules. It's allowed. It's okay. I'm driving the bus.
Wait, can you
And we're gonna-
for a second?
Can I pause for 1 second?
Go back for a second. The slide.
Oh, the slide. Sorry.
Oh, wait.
It's been more than a second.
Glad to see you got my back. Thanks, Ken. So we're going to switch to something called a definite integral. The definite integral is going to do what we were doing on the sketches. We're going to look for the area under the curve. And if we do it right, we'll get the exact area under the curve. But we're going to start by taking approximate areas, which we've already done with rectangles. But if we use that limit idea and we shrink the rectangles down, eventually we'll get to something that's going to be an exact area under the curve. We're still not there yet, so we're gonna crawl before we run here. But let's get some notation under control. Okay. Now what have we done? We've taken this big ugly Riemann thing and said, I don't want to play with all that. Let's go back to the pretty looking S-looking Archimedes. Was it Archimedes?
Yeah.
The Archimedes symbol.
Oh, did sixth grade believe it?
And let's put some numbers up on top. Well, what are the numbers? You know A and B. What do A and B represent?
Numbers.
Which
Interval.
numbers?
Interval.
Interval. So on the sketch that you did yesterday in class, what would A and B be?
0 and 3.
1 and 5 in the example, 0 to 8 on the ones that you were drawing on. So that's a fancy way of saying, I think I say it up there, find the area under the curve of f of x from the starting point A to the ending point B. Okay. The indefinite integral didn't actually deal with numbers, we stayed with a function, but now we're going to start dealing with numbers here. These are called limits of integration. Oh, it says right here. These are called limits of integration. That's the upper limit, that's the lower limit. Whenever you're doing this, B should be bigger than A, because we're going to go left to right every time. And occasionally you'll have somebody screw that up. I'll show you how to handle it if A is bigger than B. So we can start this with, start plugging in functions. We can put in x squared. But then what? Well, we can take the antiderivative of x squared, right? Mary, what's the antiderivative of x squared? Thank you, Mary. You did hear, okay. Brennan, what is it?
1/3 x to the third.
Good, 1/3 x to the third. Is that what you were gonna say, Mary?
Yeah, exactly.
Awesome,
He
good
just
job.
missed me.
Yeah, you were starting, but he was quicker on the draw. I'll give you a chance at redemption in a second. But then we get this function 1/3 x cubed. Well, what does that mean? How do we incorporate the numbers into that, and how do we use that to find the actual numerical value? Well, we don't know yet. That's something called the fundamental theorem of calculus. It's kind of a big deal when it has a name like fundamental theorem of calculus. It's pretty fundamental.
You
Do we
basically.
know it?
You will. Not yet.
When?
Hopefully it was already in your head.
I think after Thanksgiving. I don't think we do it next week.
Turkey Day is
It's
next
gonna be a
week.
big day.
Turkey Day is next week. Yes, very good.
Today.
Fun.
Thanksgiving is next.
All right, so before we start talking about how to do this, we need to get some properties under control. And these properties are similar to the properties you've seen already. The integral of a sum is the sum of the integrals. The difference of integral, or the integral of a difference is the difference of the integrals. Okay, I don't want to beat a dead horse because you've seen these properties already. I'll just give them to you. You got a constant, put the constant out in front. It doesn't affect anything. Ooh, this is a good one. Why? Why is that last one 0? Sam, you wanna take a shot at it?
Yeah, but I could be way off. Is it because the
What's the worst that could happen, Sam? You're wrong, we point and laugh at you and you have to leave and go pet the dog.
yeah, isn't it like that it's not moving anywhere? Like it's starting and ending at the same point?
Okay, so what would the area under the curve be?
It's nothing.
Right, because I'm trying to find the area of a segment, right?
Yeah.
Segments have no thickness. Okay, and again, what's gonna help you through this stuff is continually remind yourself, what am I doing? I'm finding the area under a curve. Okay, I don't care what the curve looks like, but if I have that curve, I wanna calculate that area from the curve down to the x-axis. And so that bottom one, we're finding the area from A to A, which we're actually finding the area of a segment, because there's no width, which is gonna be 0. How are we doing for time? What is this, 26?
42.
Oh, we got plenty of time. Huh. Am I going too fast? Yeah? I'll slow it down. Nice. Can I click?
No.
I wanna get to the fun stuff, so we gotta get through all this mucky muck before we do the fun stuff.
What's fun?
You'll see. I'll spoil the surprise. Is that what it's doing?
I don't know, it's like this jacket.
Take the jacket off.
No. It's so cool.
Okay.
It's really cool. I'm just
Fluffy
gonna miss
inside
it.
too?
Yeah.
How do you know which way is inside and which way is outside?
The zipper.
Oh, plus your pockets would be hanging out, you look like it's your most pockets would be flopping around on the outside.
No, look at their pussy.
Yeah, but you'd still see, and you got tags on the side, it's pretty obvious.
That's fair, that's fair.
It's not a reversible jacket.
No.
Okay.
Mr. Reedy, can you explain the second one a little bit more?
Think of it in terms of a derivative. If you're taking a derivative of 2x cubed, right, all you need to do is just put the 2 over on the side, take the derivative of x cubed, multiply your answer.
Okay.
So it doesn't affect the outcome. So just move it out in front, forget about it, take care of this business, and then multiply it by c. Yeah. Remember, c is a constant. Okay, think about this one graphically. What's happening? I'm going from A to B, and I'm saying, hold on a second, I don't need to go from A to B, I can go from A to B and stop at C along the way. Does that make sense?
Why would you do that?
Why would you do that? Bad attitude. The function might get kind of crazy. You got a piecewise function, there might be a logical breaking point in the function. For those of you that are visual learners. Okay, I want to find that area. Well, what this is saying is, oh, I can stop here and see that this plus this are still going to give me that. Make sense? Okay. However, I would point out, notice where these are located. One of them is on top and one of them is on the bottom. If that's flipped, you got some problems, but I'll show you how to fix that in a second. And also notice that C has to be between A and B. Okay. If you're going from your house to Grandma's house, and you stop at 7-Eleven on the way, you're not going to drive in the wrong direction to go to 7-Eleven. You're on the way to, that's a bad analogy, never mind, we'll just move on.
Oh, no, yeah, there's slurpees.
No, that works.
When I started, it sounded better in my head, but once I started saying it, I was like, that doesn't make any sense. Here's the big one. What if the number on top is smaller than the number on the bottom, or the number on the bottom is bigger than the number on top? Because we always want big over small. Just flip it over and put a minus sign out in front. In other words, if I'm going from right to left, that's no good. We want to go from left to right, so go from left to right. Just put a minus sign in front of it. Think of it like a vector. I think that's right, isn't it? If you have a vector going one way, you want to go the other way, you just change the sign on the vector? Is that right? Okay, it's been a while since I've had physics.
I'm sure Cam would have something to say.
I'm sorry?
So I'm sure Cam would have something to say about it.
That's why
too.
it's so quiet. I didn't notice.
I wasn't going to go there. I wasn't going to go there, but now that it's out, where is Cam?
Who cares?
It is kind of peaceful though, isn't it?
I didn't realize that.
Takes the edge off a little bit, like, oh, that's all right. Okay, all right.
Oh, wait.
Oh. Don't write down every
Okay,
word.
you're good.
You're not good, or you're still writing?
So,
Two entirely different
still
statements.
writing.
Okay, got it.
Not close to being done. Not good.
It could be on both.
It's amazing what you can find on the internet.
Yeah.
Alright.
Oh God.
Relax. It's easy. I'm not even asking you to find an antiderivative. Oh, kind of.
I'd rather find
I mean, I kind of am, but, you know,
I'd rather.
not really. I mean, you know.
Like, what are you trying to find?
Well, I haven't, this just says given. I haven't asked you a question yet. You guys are freaking out. I haven't said anything yet. Just, hey, this is true. Okay, it's given.
In the,
Okay, we done freaking?
No.
Now here's the question.
Oh.
You literally didn't have time to read it. You just, as soon as something flashed on the screen, oh. It could have said, I'm giving you all $5, and you would have been like, oh.
It's that weird F symbol.
Is that what does it for you, Sam? That's your triggering mechanism?
I mean, if it was just without the F, that'd be fine.
Yeah.
The thing that looks like an F.
what it,
I wasn't
you
gonna
did-
let it. Did you say F or S?
The thing that looks like an F. I don't know what it's called. An F
Looks like an S.
Are you saying
Oh.
F or S?
F.
As in
As in
ferret
frog?
or salamander?
Yeah. As in fraud. Like,
How does it look like an F? So confused.
Okay, so Abby just asked a question. What are we doing?
That's what
What's
I'm
the
trying
goal?
to read.
I could graph that function.
No thanks.
I have no idea what that function looks like. So let's not graph it, okay? If I could graph it though, I could draw a picture and find the area under the curve. That's what I'm trying to do, right? Okay. And I'm from 2 to 4. Is that you, Casey?
Yeah.
Good, from 2 to 4. So I want a chunk of that graph from 2 to 4. But since I don't know what the graph looks like, I don't have a 6 and 1, I don't have a picture, blah, 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 I gotta find a different way to do it. So applying the properties that were on the last couple slides, we can start, and it's just like when we did derivatives. Remember, when we started derivatives, you took the derivative of x squared, for instance, and then I said, okay, now do x squared plus 7x. Well, you just did them as individual terms. You took the derivative of x squared, you took the derivative of 7x, and you were done with it. Same thing is true with integrals. So I'm going to take the antiderivative of 10, I'm going to take the antiderivative of 4x, and I'm going to take the antiderivative of 3x to the third, okay, from 4 to 2. Well, since we don't know how to do that, I've got that information up here. Does that make sense? Okay, so look, this is a big jump. This would be the point where you go, oh. Okay, good. This is a constant. So I move the constant out in front and take the derivative of this. What's a derivative of 1? Sorry, what's the antiderivative of 1? X, right. What's the antiderivative of x? Well, I don't care because I gave you that information. That's right there. And what's the antiderivative of dx? Again, I don't care. I gave you the value. What's the antiderivative of x cubed? Well, we know from what Brennan told us before that it's 1/4 x to the 4th. But again, we don't care because I gave you the information that you need. We still don't know how to handle these two things. Okay? These numbers are, eventually we'll learn how to actually calculate this. But since we don't know how to calculate it, I'm chopping out that step for you and just telling you, yeah, it's equal to 60. Then it just becomes a matter of plug and chug. Boom, 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 boom. Okay, 10 times the value 2 came from over there, 4 times the value of 6, which is over there, and 3 times the value of that, which is 60. Okay?
Will we have to find out, like, later in time what we're given?
Oh, yeah, later on I'm not giving you this.
Okay.
You're going to have to go from here and you'll be on your own.
Fine.
Hey,
Never mind.
anything bothersome up there?
It's negative.
What's that?
It's negative.
Why is that bothersome?
I have no idea. I was just guessing.
Wait.
Yeah.
So you put the constants out in front.
Yeah.
Why do you have the dx for the 10? I don't know what I'm asking. Never mind.
Okay, here, let's do it this way.
Oh, you know what? No, I get it. Never mind.
Like what is that? Like what is it? Yeah, what is it? Like
I get it.
Okay, but I'm going to do it anyways.
Okay.
What does, where'd it go? What does this function look like? No, just, sorry. And I know I'm not actually covering it up. What does that function look like? It's a straight line at 10. Okay. So what am I asking you to do? I'm asking you to find the area under this curve from 2 to 4. What's the area of this rectangle? Delta x is 2, the height is 10, 2 times 10, 20. That's the easy one. Now I could draw, what's the graph of x look like? What kind of line? Yeah, that line, right, the 45-degree line. Okay, so if I get rid of this, pretend that's 45 degrees. Ooh, what shape is this? It's a trapezoid, correct. You can find the area of a trapezoid, right?
Like you can, but like what is
What'd
it?
you have for dinner?
I had you.
I had
Oh.
you, technically.
I blame myself.
I technically had you.
Is there?
How?
That's how I did.
Oh,
She
yeah.
counts as like you.
Nice.
Wait.
Like not like.
Because we used to take your, we took your quiz
quizzes and everything.
She sat in here for us.
You know, I didn't get a dollar from all that work. She took all my stuff and then contacting my lawyer. Okay, how about this one? This is the x cubed part of it, or the 3x, well, whatever, it's close enough to 3x cubed. How about this area? Oh wait, we can't find that yet, can we?
Try our best.
60.
What is it?
60.
Good job. How'd you know that, Kev?
Given.
Yeah, it's written right up there. Good job.
That's
At least somebody's paying attention. Okay, so eventually, if we look at simple functions like 10 and x, we can break that into things that we can manage. If we look at something like x cubed or rational functions or any of these other ugly functions we've done, we still need to get some work to figure out what that means. Yo,
Will it always be given, or is there gonna be a time when we have to?
no, it won't always be given. Eventually, you're going to be able to do this just as it appears. But in order to do that, you need to know the fundamental theorem of calculus, which we haven't done yet.
Okay.
But easy peasy.
I think there should be like deja vu.
How come?
Yes,
we
Brendan.
How come when we found the area of the thing under 10 and it was 20, but it says 2? Did you switch?
Oh, because I don't have the 10 here. So we could have done this, and this is just 1. So I'd have a line at 1, and then go from 2 to 4 would be 2 times 1 would be 2, and then times the 10. So I threw the 10 in there just because I was feeling saucy. Okay. Let's go back to this.
No, because I just don't know what 136
You just-
means.
You just don't, is that a problem?
Oh,
Why is it
wait.
negative?
No,
Well, that's what I'm asking.
like, why says you
Maybe
made fun
it's
of
just
me.
below.
No, I didn't make
Yes,
fun
you
of
did.
you. If I make
Why
fun
does
of
that
you,
matter?
that would be making fun of you.
You're like, well, why does that matter?
Well, that's what I'm asking. Why does it matter? I mean, if I remember correctly, in geometry, that wouldn't make any sense,
We're not
right?
in
If you're
geometry
given
anymore.
the area of a circle and you come up with negative 4 pi, you're going to get it marked wrong. That doesn't make any sense. Area can't be negative. Did I screw up? Or is there something else I need to explain? Did he?
Is it like, so like if those are like the areas on top, and obviously they're gonna cross and they're gonna overlap each other, but at some point there's gonna be like an area where all of them, or there's like an area where they're all underneath the line. So
The
I
curve.
feel like, yeah, the
Curve.
curve. So I feel like you just take that number and then do something with that number and then you'll find your answer.
That's great. The only problem is the do something part of it is the catch.
You could add it, you could subtract it.
You show up in the morning, you do something on that AP test, and then you get a score.
That's true though.
Right. So, and you're right, because we don't know what that something is yet for this part. For this part of it, we'll find that out later.
Because you can like draw, so we could draw a picture.
So this is not normal. This statement, because we haven't ever done this before. You haven't ever done this before, where you get a negative area. And simply put, if the function ends up below the x-axis, we consider that a negative area. Above the x-axis, positive, that's fine, makes perfect sense, because you've always done area to be positive value. But now if it flips over below the x-axis, you'll have a negative area. So on that previous problem, if you did look at the graph of that function that I had up there, and knowing that the definite integral is negative, what can you tell me about the graph? Is the whole graph underneath the x-axis? No. Well, then how's the answer negative? Yeah. Part of it / the majority of the graph has to be below the x. The area below the x-axis has to be bigger than the area above the x-axis. Okay. Good. Quick reminder, you should know these three. If you, are you all writing them down? I just said you should know.
I don't know what trapezoid.
You don't know a trapezoid?
I always know.
Trapezoid.
Trapeze.
No, that would be an A. Trapezoid.
You could say
trapezoid.
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 But it's trapezoid. It's a silent E. You know, so like
Silent E, I-
cat, but then if you put an E on the end, it becomes Kate.
Oh my god.
So why is it just trapezoid?
Like if it's Pat, then they would get
It's
pate.
not right.
Wait.
Like,
math
class,
class,
English class.
Like,
Trust me, I wouldn't.
But
I wouldn't like it.
it's
Did
as.
he?
Trap
I was
as.
so confused because I thought
You know, like all that nonsense in geometry where it was like rectangle's a square, but like some rectangles are squares, but not all squares are like that.
Oh,
it's the other
your
way around.
favorite always, sometimes, never problems?
Yeah, well, those apply here. Like when we have to like legit question like on the AP test. So like if they give us a trapezoid, it's gonna be clearly a trapezoid. If they give us a rectangle, it's gonna be clearly a rectangle.
Yeah,
Okay.
but there's also rectangles in trapezoids.
But there's also triangles and trapezoids as well.
Correct.
Like that stuff's okay. It's just the
Oh,
ones where
okay.
it's like
It's like the
like-
dogs and golden retrievers thing.
yeah,
Right.
those are dumb. But yeah.
Okay.
All dogs are-
So if it pops up on the AP test, just write dumb next to it.
I will.
So to clarify, trapezoid, trapezoid, same thing, right? I thought you were talking about an entirely
Two parallels. Two parallel segments with sides on it. That's a trapezoid.
For
Yeah.
the past, literally yesterday, I was thinking it's like a trapezoid.
Well, why wouldn't you ask?
Because everyone like knew it, so I was like, maybe.
I
No,
guarantee
we all
that.
don't know it either, Abby. We all throw the dart on the dartboard.
Okay. We did something like this already. This is going to be the graph of a horizontal line. We're looking from 1 to 3. Bing, we get a rectangle. Okay. What about this guy? Well, we did something like this. What is this going to be when you graph it? It's going to be a trapezoid, correct. This is a line with a y-intercept of 2, so it's shifted up. It goes up at an angle of 45 degrees. The area below it would be a trapezoid. What about that guy? It's that thing. Which this? Wait, hold on. Are you saying this thing or this thing?
No, this thing.
This thing?
Yeah.
No,
Wait,
it's the other one.
this thing?
It's this thing.
Wait, that's what I said.
No, you're saying this thing. Oh, hey, hold on.
No.
I can't wait if Cam ever watches this video. He's gonna be like,
Yeah, he's not gonna watch.
are you saying that thing?
No.
You're
that-
saying, okay, hold on. You're saying this thing.
Unless I say we talk.
Correct.
Not that, yeah, that. Come
Correct.
on.
This one.
Yeah.
Good. That is correct.
Okay.
Okay. What is this?
Maybe.
Yeah, that's maybe.
Yeah, that's whoa.
Wait, now
That's a square root of x. This is a semicircle. Remember, this is a semicircle with a radius of 2. Right. Top half of a circle, aka semicircle. Top half, radius of 2. Can you find the area of a semicircle?
Yeah, isn't that just easy?
no.
Yeah. Find the area of the circle. Divide by 2.
Yeah.
Yeah.
It's like, do
What?
they-
Do you think I'm trying to trick you into something? Like I'm teaching you something wrong?
Yeah.
Like there's a sinister plot at large here that's gonna
Oh, for
just find the area of a semicircle. What is this equal to then?
1/2 of the area of a circle.
What's the radius? 2. So the area is 4 pi. And boy, Kev.
I'm not gonna be able to do that.
Yes, you will.
It's a one-time thing.
Are we gonna have to do trig now?
No, I don't. Do you want to do tricks?
No.
I can make one up.
Wait, ask him.
Okay, so there's the rectangle. Easy peasy. There's the trapezoid from the line. Notice this is a trapezoid on its side, so that's base 1, that's base 2, that's H. Just as a clarification. This doesn't matter. You gotta look at it like this. Okay. B1, B2, huh.
Does that matter? Yes, it does matter.
Don't roll your eyes.
Every time we're like.
Wait, where are you? Go back, because that might be a question. So, no, I mean on the trapezoid. I'm just, so
Yeah, so now I have to go do
you just wrap it to find that 3, the 2, and the 5? Okay, I just want to make sure that you aren't like somehow pulling it from the equation or
You
something.
could pull it from the equation if you'd like.
How?
Put 0. Put 0 in here. 0 plus 2 is 2. Whoosh. Put 3 in there. 3 plus 2 is 5.
Oh, okay, yeah, and then the, yeah, okay, thank you.
Oh,
Oh, God.
oh, yeah, come on. No trig at least. Anytime you have to take the integral, and I mean literally anytime you have to take the antiderivative of an absolute value function, draw a picture. Because it's going to break it into some triangles. Find the area of the pretty purple region, find the area of the ugly brown region, add the 2 up. What?
I know he puts this, so the antiderivative is just the area underneath
Right.
the function.
Antiderivative is the integral, which is the area under the curve,
So they're all
from the
same
function
thing.
down to the x-axis.
So they're all the same thing.
It's all, it's all synonymous.
Yeah, 'cause I was confused of like, you had like the integral equation and like same thing with Grace, like I was wondering like where did that play in, but they're all the same thing.
Yeah.
Okay.
Okay, we good?
Wait, can you explain how you get that?
Yeah, I just graph this. Okay, that's the v, that's your standard absolute value. And then the integral means find the area under the curve from -3 to 2. And when I draw these vertical lines like I used on the rectangles, it breaks it into 2 different triangles. Because this is the area under the curve from the curve down to the x-axis. These numbers, count, this is 3 units, and then I found this distance by plugging it into the original function. The absolute value of -3 is 3. Wait, hold on, we're not done. The absolute value of -3 is 3, so that gives me this height. So this triangle is 3 by 3 times a half, 4.5. This triangle is 2. The absolute value of 2 is 2, so it's 2 by 2 times a half, which would be 2. Add the 2 up. Okay? All right, we're good. So you know what's going on tomorrow. Test corrections are due at the end of the period tomorrow.